Which brings to our next topic, which is entanglement. So, what is entanglement? Well, simply speaking, it's easier to say that what is an unentangled state, or state which has no entanglement, state without entanglement. Essentially, any quantum state that can be expressed as a tensor product on two systems. This is an unentangled or a product state. So this is a tensor product, as we discussed in this lecture. So any state which is a tensor product state is also an unentangled state, or in other words, a product state is an unentangled state. And if a state psi cannot be expressed as a product state, or in other words, a state psi cannot be factors as tensor product state on two subsystems, this is called as an entangled state. So in other words, an entangled state cannot be factorized as a tensor product. So this basically can be extended. This was for a bipartite system, naming a subsystem of a composite system of two parties, but this essentially can be for a many party system also, a composite system, so on and so forth. So this is a composite system of 4 parties, and what I've written is as this is a product state of a system, let me call it a 4-partite system. And for a system of 4 parties or a 4-partite system, any state that cannot be expressed as a product is going to be an entangled state. So the next question which arises is that, okay, we've answered a binary question, entangled state versus a product state. Now, among entangled state, how do I quantify the amount of entanglement? So in other words, I know now that a state that is not a product state is an entangled state, but what is the degree of entanglement in that state? Is it like nearly zero entanglement, or it has nearly maximal entanglement? In general, that's going to be our focus, and for that we come to something called as the Schmidt decomposition. So I'll first state this theorem, which states that suppose, so right now our focus is going to be bipartite entanglement, or in other words, entanglement of 2 parties. So suppose a state psi is a state of a composite system AB. Now one can show that there exists an orthonormal state or orthonormal basis IA for system A and an orthonormal basis IB. Notice I'm using the same index for A and B both, and that's essentially the idea on system B of system B, such that I can express my state as a linear combination of the tensor product of the states on system 1 and states on system 2. In other words, notice I'm using this should be I. I'm using the same index, and that's essentially the idea that any state can be expressed in this particular form where index IA is the basis on subsystem 1 and index IB is the orthonormal basis on subsystem 2, and where lambda I are non-negative real numbers satisfying, they are normalized in some sense. So this is called as the Schmidt decomposition. So what did I do? Again, I can repeat that we started with a state psi, and any general state, how would I expressed it as Cjk Jk. By definition, I can write any tensor product state on a composite system AB as a linear combination sum over J and K tensor product over these two vector spaces. Now, the essential feature of Schmidt decomposition is that this state is equivalent to sum over the same index, a tensor product over two Hilbert spaces. So this transformation is called as the Schmidt decomposition. And this Schmidt decomposition is very important in order to understand entanglement, as we'll see. But how do we, first of all, how do we show this? How do we show that this indeed holds true for any state? So essentially the idea is to show, let's assume that the dimensionality of system A is equals to the dimensionality of system B. The case where dimensionality of A and B are not equal is a trivial extension of the proof. So let's just prove it for the case when both systems have the same dimension. In other words, my matrix C, which comes over here with element Cjk, is a square matrix. Now, what we do is, the idea is to decompose this square matrix into its singular value decomposition. So square matrix into its singular value decomposition, which essentially means that I'm going to write each of these matrix elements Ijk as so. Firstly, what does a singular value decomposition mean? It means that I'm going to decomposing this matrix C in terms of a product of three matrices where U and V are unitary matrices and D is a diagonal matrix. And we can show that any square matrix can be given a singular value decomposition, which means a product of a unitary matrix, a diagonal matrix, and another unitary matrix. So this is called as the singular value decomposition. Now, how do we show it? Well, the idea is that we just need to, writing in terms of the indices, we need to show D, remember, is a diagonal matrix, so same index, yeah. So essentially, this is what the singular value decomposition looks like, where I'm summing over the index I over here, and that's going to give me Cij. So for now, take it as a theorem that assuming that given that I have the SVD or the singular value decomposition, then, well, it just turns out that how am I going to express the state? Well, the Cjk's over here are the coefficients of Jk over here. So I'm just going to express my quantum state as I'm just going to express the sum, which is going to be so this is just expanding the coefficient Cjk using the singular value decomposition, and now the summation of this entire quantum state psi is on j, I, and k coordinates. So, well, once I have this, now it just boils down to relabel my variables or relabel my indices again. So, in other words, what I'm going to do is that convince yourself that this quantity over here, this product, combining this with this guy, that is just another unitary matrix applied to these column vectors and summed over the coefficients. That's just going to give me another vector. So, well, this was I over here, Ji, remember? Yeah, so J sums over, what am I left is with is Ia. This is a vector. Similarly, I have Vik, k, I'm combining this guy and this guy, and the sum is over k. That's going to give me another vector I. K is the dummy index I summed over. What is going to be left is my index, which is not summed I over here. So I've got two basis vectors on Ia is a basis vector or an vector on subsystem A. Ib is a vector on subsystem B. And in other words, after relabeling these bases, what do I have? I absorb the D's into my lambda i's, so I'm left with nothing but Ia, Ib. So I started with a state psi. I was able to express the state as the most general description of a state I can write in terms of two indices j and k over two subsystems and a linear combination over them. And then using my singular value decomposition, I was able to write it as UDV. That's my singular value decomposition. I renamed my states after summing of a unitary matrix over a set of states J gives me another vector, and similarly VIKK summed over K gives me another vector on the Hilbert space B, and this is my singular value decomposition after, and this is after singular value decomposition. This is called as the Schmidt representation of the quantum state. Okay, so there's an exercise for you guys to indeed convince yourself that this state I over here, which was nothing but U J I U J I J, this is indeed an orthonormal basis. How are you going to show it? Well, one way to do is to invoke the unitarity. Since U is a unitary matrix, unitarity of U, and of course that J's over here were an orthonormal basis to start with. So in other words, what we mean is that I already know U dagger was I. Let's say I have one I can express it as UJI sum, and let's say I have another state K, which was a linear combination over the basis K. Now the inner product Ki is nothing but U Kj dagger. Remember, I'm taking the inner product Uji J over J, which essentially gives me a Kronecker delta function. So this is just invoking the unitarity property, and this is going to give me an orthonormality condition on the new bases I have formed from the previous bases. So in other words, my Schmidt decomposition, which was expressing my state psi given by U J I D I V I K. Remember, this was my Schmidt decomposition, and this is summed over all the indices, which gave me the Schmidt form. The bottom line is that the bases over here, these are orthonormal bases, which we just showed through this transformation. Similarly, we can show that the set of bases IB is also another orthonormal basis. So given this fact that I have a Schmidt decomposition for any state, now can you tell me, under the Schmidt representation or the Schmidt decomposition of a quantum state, what about the entanglement? So remember that we already discussed that a state is entangled when it cannot be expressed as a product state. Well, just imagine if in this Schmidt decomposition, all I have is only lambda 1, for example, to be non-zero, rest all lambdas are 0. So in other words, I have let me assume that my, well, I goes from 1 to, I don't know, did I mention d? So let me say lambda 1 is 1 and list lambda I all other for all I not equals to 1. So then, well, my state is just 1, 1. And this is a product state. So a state is a product state or is not an entangled state when the Schmidt coefficients or the lambda i's only has one non-zero Schmidt coefficient, implies a product state. If I have Schmidt number or the number of non-zero Schmidt coefficients is also called as a Schmidt number. If the Schmidt number is greater than 1, that implies an entangled state.